Well, to complete the look at the logarithmic function, we're actually not going to look at how to integrate the log function. We'll see that in extension 2, x log x minus x, by the way. But what we will look at is integrating derivative on function, because what we saw yesterday was when we differentiate a log, we got derivative on function. So logically, if we're looking at fractions where we have a derivative on top and the function on the bottom, if we can create that fraction, then we know, the answer is going to be the log of whatever the denominator is. So that's the key. We want to try and create the situation where we have derivative on function. Okay. Now, if you didn't notice it straight away, because obviously the derivative of this is -3, not 1, so maybe you wouldn't notice this straight away. What you would automatically do, I guess, is put it into index form. Now, if you put this into index form, you'd have 7 minus 3x to the power of -1, and then we go, add 1 to the power over the power. Oh, hang on, if you add 1 to the power, that gets you 0. Can't put 0 on the bottom of the fraction, so that should be like a little signal going, something else is happening here. You surely can't do that, so it's probably going to be the log situation. Let's create the derivative on top, so I'll put -3 on top, but I can't just change the question, of course. So to balance it out, I'll multiply it by -1/3. But I've now got derivative on function, so I know that will be the log of 7 minus 3x when we integrate that. Plus, of course, a constant. Technically, the integral is the log of the absolute value of function x, because you can't find the log of a negative number. Now, okay, so if we look at our hyperbola over there, if we wanted to find the area under the curve, now if I'm on the right-hand side of the y-axis, not a problem, because I'd integrate the 1 on x and I'd get log x. I'd sub in, let's say we were going from 1 to 2. Sub in 2, log 2, minus sub in 1, log 1, I can do it. But if I was on the left-hand side, I'd integrate 1 on x, I'd get log x. And say I was going from -2 to -1. I go, log of -2, hang on a sec, can't find the log of a negative number. Reality is it doesn't actually matter though, because if you're doing a definite integral like that, you could use your log laws, and you'd have log of -2 minus log of -1, you combine them together and it becomes +2 anyway. So that's why the absolute value, technically yes, it's absolute value, but if you're working with definite integrals, unless of course for some reason you were integrating over the discontinuity, which is not something we really look at, then it's not going to be an issue. But yeah, so you will see in some answers log of absolute value. Okay, let's do the next one. dx on 8x plus 5. Once again, we want to create the derivative on top. 8, balance it out with an 8th out the front. We have an 8th of the log of 8x plus 5. I guess when you're looking at these fractions, the other thing you're looking for when it's polynomials, if the degree of the one on top is 1 less than the degree on the bottom. Because when we differentiate polynomials, we know we reduce the degree by 1. So that's the other indicator that, this is probably going to be a log. So the derivative of the bottom would be 6x to the power of 5. So let's put that there, balance it out, and we get a 6th of log x to the 6 minus 2, plus, of course, a constant. Now here's an interesting thing what happens with the integration. Integrate 1 over 5x. Well, okay, I'll create the derivative on top. I get 5 on 5x, but balance it out, a 5th out the front, integrate that, and so we get 1/5 log 5x plus c. But I could have done it a different way. I could have factorised the 5th out first, and then I integrate the 1 on x, and I get, a 5th log x plus c. How can I get 2 different answers? What's going on here? It's the constant, yeah. I mean, I've just put plus c because of it's a constant, but they're actually different constants. Because in the first one, I could have used my log laws to rewrite that to be a 5th log 5 plus a 5th log x. Well, a 5th log 5 is a constant number. So it gets absorbed in the constant in the second one, and you've got the 5th log x. So they are actually the same answer. That's where sometimes when you're looking up your answers, when you're doing the questions, you look at the answers with these ones and you go, I got it wrong. Maybe. You might not have. So it might have just been how they approach the situation. Oh, 4x plus 1, 2x plus 1. Bit hard to create the derivative on top of this because I've got a linear function on a linear function. So whenever you see one of these where the degree of the top is the same or more, before you do any integrating, do a division. And just in case you don't see it straight away, I've actually done the long division on that one. So it ends up being 2 with a remainder of minus 1, so we've got minus 1 on 2x plus 1. And we then get something we can integrate. The 2 obviously goes to 2x, and the other one can become derivative on function. So we have 2x minus a half of log 2x plus 1, plus, of course, a constant. Let's do a definite one. Oh, how nice. The derivative is already there. I don't have to do anything. 2x is the derivative of x squared. So log of x squared plus 1, sub in the 2, sub in the 1. Yes, that's an exact answer, but when the coefficient of the logs are the same, use your log laws, pull it into one thing. So that would be the log of 5 on 2. Now, if the coefficients were different, I probably wouldn't worry about it, depending on how different they are, I suppose. Differentiate x cubed log x, and hence integrate x squared log x. Well, if I had no idea how to do this question, I'd cheat. And I'd say, well, the integral of x squared log x, that just might be x cubed log x. Or some multiple of it, of course. Because why did they ask me to do that? So if you do get caught in that situation, I mean, you might not be right, but at least it's better than leaving it blank, I suppose. At least you can get something out. So all right, let's do it. And in fact, you'll see that actually, no, it doesn't work out to be that. But differentiate x cubed log x. We write down the first, diff the second, write down the second, diff the first, tidy that up, and we get x squared plus 3x squared log x. So it's close, but it's not x squared log x. However, what I do now know is that when I differentiate x cubed log x, I get x squared plus 3x squared log x. Therefore, when I integrate x squared plus 3x squared log x, I will get x cubed log x. Well, I don't actually want all that integral, but remember, with integration, we can split it up into individual parts. So I can actually move the integral of the x squared to the right-hand side. So 3 lots of the integral of x squared log x would be x cubed log x minus the integral of x squared dx. So divide everything by 3, but also integrating the x squared, and I get my answer. So had I tried to cheat with this one, it wouldn't have worked. But it's still a pretty good guess, I suppose. So 12D and 12E, there's some integrations to do, but then of course applications of integration. So there might be some volume questions, there might be some area questions and things like that, all the uses of integration that we've seen so far.